Welcome back to this Computer Science 1 video series. In this part, we'll cover a powerful debugger tool called GDB. A debugger is a program that simulates or runs another program that allows you to pause and resume the execution of a program, set breakpoints or conditions where the execution pauses automatically so that you can look at the program's state, view variable values and watch variables for changes to their values, and step through a program line by line or even instruction by instruction if you wanted to look at its assembly code. The debugger that we'll use and demonstrate is the GNU debugger, or simply just GDB. To use GDB, you'll need to compile your program using the G flag. This preserves a program's identifiers and symbols so that as you're debugging, you can see the original function and variable names. Normally these are lost when the program is compiled. The G flag preserves them. Then you start GDB with your executable as follows. Optionally, if your program requires command line arguments, you can provide them at startup using the following. These can also be set inside GDB after you've started. Here's a list of commands that we'll demonstrate. Additional resources and GDB cheat sheets have been provided on the course website. Let's take a look at a full demonstration. Here I've got a buggy program. The purpose of this program is to compute the sum of the first n prime numbers. Optionally, it allows the user to provide n as a command line argument, but defaults to 10. We have several functions here, including a sum function, a function that returns an array containing the first n primes, and a function to determine whether or not a given integer is prime or not. There are lots of intentional bugs with this program. So let's get started debugging it. I'll go ahead and compile it with all these flags. I'm using the W flag instead of the W all flag to suppress all the warnings. Some of the warnings are going to give our bugs away immediately, which is good in practice, but I want to demonstrate the debugging tool here. When I run it, it simply gets stuck in an infinite loop. So let's go ahead and start up the debugger. It will be useful to see our code. So I'll type layout next to display it. There's nothing here yet because the program's not running. So let's start it by typing run. It is running, it's stuck in the infinite loop. If we interrupt it using Control-C, then we can see that we're getting caught in this while loop on line 57. To demonstrate that we're getting caught here, I'll go ahead and use next to step through it line by line. A shorthand version of this is to simply type n. Now, to understand what's going on here and why it's getting caught in this infinite loop, let's go ahead and print out some of these numbers. I is 0, which it received on line 55. N is 10. X is 2. So we never get past the first iteration. Clearly the problem is probably in the isPrime function. Typing next is simply going to go in this loop. What I want to do is I want to go into the isPrime function. So instead of next, I'll type step. That takes me to the isPrime function. And I can continue with next or step. The difference is that next goes to the next line in the immediate scope. Step will actually step inside of a function so you can take a look at what's going on inside of it. X is 2 here, which is a prime number. But we're returning false. We found our first bug here. The intention here was to get rid of all even numbers. But 2 is an even number, but that's also prime. So let's rethink our design here. To quit out of the debugger, simply type quit. Now let's look at this a little bit closer. This function is supposed to return true if x is prime and false otherwise. The for loop is testing whether or not x is divisible by any odd integers, starting at 3, going to 5, 7, etc., up until the square root of x. So that seems right, but again, one of the corner cases is when we've got 2. We need to return true because 2 is a prime number. Let's take care of it with an additional conditional statement. Some other corner cases that we might not have thought of would be 1, 0, or any negative numbers, which can sometimes be thought of as prime. For the purposes of this program, let's go ahead and take care of that now. Otherwise, the loop looks fine. Let me go ahead and recompile. And we're still stuck in an infinite loop. We're still stuck here. But let's take a look at the variables this time. I is now 1. And x is 4. So we did get past that first iteration. I've stepped into the isPrime function again. We would expect it to return false. And it does. The problem is no longer in our isPrime function. Instead, it's a problem within our loop here. The intention of this function is that we find the first n primes. 2, 3, 5, 7, etc. We return the result when I has reached n minus 1, and we found n of them. We found the first one. Indeed, I can print out the result here. But we haven't found the next one. To see what's going on here, I'm going to set a breakpoint. I'm going to set a breakpoint the first time I come into this function. And I'll restart the program. Now sometimes the TUI mode or text user interface mode screws up the display like this. If that happens, don't worry. Simply type refresh and it'll all be good again. N is the default of 10. We've initialized I and X. Now while I is less than n, while we've not found the first n primes, we execute this loop. X is 2, so this will return true, and the if statement executes. We assign 2 to the first value in result, and increment our I because we found one element. But here's the problem. We go up by 2, meaning that we'll only ever hit all the even numbers. We need to rethink this function. The problem here is that 2 is again a special case. We should always include it, and then handle the rest of the primes separately. We'll always set the first prime to 2, and then we'll start at the second prime, starting our x value at 3. Now if something is prime, we'll store it, increment our index value, and then increment x up to 5, 7, 9, etc. Not all of them are going to be primes, but now at least we're not going to be stuck on 4. Once again, we're stuck in an infinite loop. Let's fire up GDB again. Let me go ahead and reset that breakpoint at getPrimes. Everything is as expected. So let's go ahead and go into the loop. 3 is prime, so this should return true, and it does. So we set it, increment I, and go on to 5. Before I continue, I'm going to go ahead and set a watch on this variable. Now I don't have to continually print it out. Anytime it changes, it'll tell me that it changed and what it changed to. 5 is prime, so we set it, increment I, and increment X. X has changed from 5 to 7. 7 is still prime, so it changes to 9. Now, is prime of 9 is going to return false because 9 is not prime. And there's where we get stuck. The problem is that we're incrementing by 2s only on primes, which worked for the first few of them, but it doesn't work after we hit 9. So we found yet another bug. Incrementing X should be done unconditionally in the loop. Let's run it again. Awesome, we've resolved all of the infinite loop problems. However, 29 is the wrong answer. This is a bit of ad hoc testing, but I'm going to use Wolfram Alpha to see how wrong it is. It should be 129. So let's fire up GDB again. This time I'm going to start from the very beginning. I'll set a breakpoint at the main function. This way I can walk through the program from the very beginning. Now I didn't provide any command line arguments here, so argc is only 1, the executable file name. Let's go ahead and skip over this, since I believe that we've taken care of all the issues within getPrimes. Before we go on, I want to see what that returned. To print the contents of an array, you need a little bit different syntax. @10 provides information about the size of the array, so that it can treat each individual element separately. Here it's just a bunch of memory addresses. Because it's an array, we also need to dereference it. We dereference it and tell it to treat it as if there are 10 elements in the array. 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. There are 10 primes, and those indeed are the first 10 primes. So we've already made some headway here. I no longer have a suspicion that the problem is in getPrimes or isPrime. In other words, everything looks okay up to this point. So let's continue. Now, there's the sum of 29. So I've narrowed it down to a single line here, or a single function in particular, the sum function. There's something going wrong inside that function. I'm going to clear my breakpoints. And I'm going to set a new breakpoint in the sum function. And I'm going to rerun the program. Here I am in the sum function. Let's make sure that we receive the array correctly. We received the array correctly. Now, I and total are correct, but remember, uninitialized variables could have garbage values. Now let's run through this loop. It seems to be running normally, but let's go ahead and put a watch on our total. Immediately we see that it's 3, which is wrong. It changed to 5, 7, 11, 13, 17. It seems to just be getting the value stored in the array. Now if you look really closely, you'll see the problem here. Equals plus instead of plus equals. This is syntactically correct. What it's doing is it's saying, let the total be equal to whatever is stored in the array, positive. In other words, putting a plus there is syntactically correct because it's similar to putting a minus there to make a value negative. But in this case, we're just making it positive. So again, let's fix both of those issues. We'll initialize total to 0. And we'll fix the operator. And now we're getting it right for that one particular test case. The first 10 primes summed to 129. Let's try it out for others. The first 10 primes are 129 still. The first 20 primes are 129. The sum of the first 30 primes are also 129. So something's going on here that you might have noticed before. Let's go ahead and fire up GDB. Now I already showed you how to set command line arguments before, but once you're in GDB, you can use set args, and let's go with 20. The first one that we know is wrong. Let's set a breakpoint at the main, and let's run it. So now lines 33 through 35 should be taking into account that we've provided a command line argument. argc is now 2. We've provided 2 arguments, the executable file name and 20, the number of primes that we want to sum up. But that doesn't get executed. Again, it's syntactically correct to use the single equal sign here, but that's not what we mean. If argc is equal to 2, then we start looking at the arguments. We actually would have caught this if we had bothered to use the WALL flag. Now you might see some other problems here too. Typically finding a bug in a program will immediately lead you to other bugs. But let's run it through GDB again. You can see the arguments that we've also provided. Now argc is correctly being checked for 2. But line 34 had no effect. That's because of 2 issues here. We're calling the A2I function, but we're not doing anything with it. In fact, the compiler warned us about that. We're not assigning n to the value returned by A to I. Here's our first segmentation fault. I'm not setting a breakpoint here. I want it to segfault. Here's another useful command. Backtrace tells me exactly what functions have been called and prints out everything in one command. The segmentation fault occurred on line 34. N is 10, primes is an uninitialized memory address, and S, which is declared down below, has not yet been assigned a value, so it gets 0. Let's print out our arguments. Remember, there are only two arguments. We can print individual ones. argvis of 2 does not exist. Its memory address is actually 0, which is the null memory address. Hopefully you saw that, but I wanted to walk you through the process here. It should be argvis of 1. Don't forget to regression test. That is, test the test cases that you knew passed before. After making changes, make sure that those changes don't break those passing test cases. Now, I don't know if that's right, but I'm going to go ahead and consult Wolfram Alpha again. And it seems correct. $1,593 is also correct. I wonder what the sum of the first 10 million primes is. It's a segmentation fault. Let me go ahead and change it so that we're not suppressing all the warnings. There's still a problem in the getPrimes function. It's complaining about us returning result, which is a statically declared array. Recall that in general it's dangerous to return a statically declared array since it may be destroyed when the stack frame is popped off. But also, 10 million values is too large for the stack, resulting in the stack overflow and the segmentation fault that we encountered. If you want to make this program more robust, you need to make this a dynamic array. And now the warning goes away. And it'll actually fit. Let's consult Wolfram Alpha. That's a different number. But that's also expected. Look at the magnitude of that number. It's over 62 billion, which is way larger than the 2.147 billion that we can hold in an int variable. So now it's no longer a bug, but instead a design issue. If we want to hold numbers this big, we need to rethink about the types that we're using, or we need to bring in an external library that supports arbitrarily large numbers. The final example I want to give you is what happens when we've got the first 10 million primes. Now it's going to overflow just as before, but also it's going to take an extremely long time to do this. That's because the algorithm that we're using to determine whether or not something is prime is called the sieve of Eratosthenes, which is an exponential algorithm, meaning that it takes an extremely long time, even on small inputs. In fact, I would not expect this program to execute within your lifetime, even if it gave you the correct results. We'll revisit the issue of complexity and efficiency later on.